Welcome to the deep dive. Today we're plunging into a really fascinating collection of materials.
Yeah, all centered around aircraft materials and hardware.
Exactly, and we're drawing from a comprehensive EASA Module 06 document.
Think of it as your personal shortcut, really.
Right, to understanding the nuts and bolts, quite literally, of what keeps aircraft up there and, how they're maintained.
And for you, the lifelong learner, the person who really likes understanding how things work.
We're going to unpack the core concepts, right?
Yeah.
Highlight some surprising details, maybe connect a few dots.
In a way that's hopefully both informative and, well, engaging.
Our mission is pretty simple. Leave you feeling well-informed, but not totally overwhelmed.
Okay, so our sources today cover a huge landscape. We're talking ferrous and non-ferrous metals.
The backbone of so many aircraft structures.
Absolutely. Then there's the intricate world of composites, those high-tech blends.
Incredible strength and lightness there.
Definitely. We'll also look into the science of corrosion.
Ah, the silent enemy of metal.
Right. And the surprisingly complex world of aircraft fasteners.
Everything from rivets to specialized bolts, yeah.
And we can't forget the enduring craft of wooden aircraft structures.
Still flying.
And even the fundamentals of electrical wiring and control cables, kind of the nervous system of the machine.
Our aim here is really to pull out the most crucial insights, those aha moments,
And the practical knowledge embedded in these pages.
Okay, let's unpack this.
So, aircraft repair. It demands a huge variety of metals, doesn't it?
It really does. It's all about finding that right balance. You need strength for flight loads.
But you have to keep the weight down for efficiency.
Exactly. And then there's durability against the elements and fighting off deterioration.
And it's not just the type of metal. The form it's in is also critical for different applications.
What's fascinating here is how they choose different metals for really specific roles based on their properties.
Let's start with ferrous metals, specifically alloy steels. These are true workhorses in many structures.
Right, known for things like malleability.
That's being able to hammer or press it into shape.
And ductility.
Which is the capacity to be drawn out or bent without breaking. Think about it.
Ductility must be crucial for parts that take sudden shocks, right?
Yeah, exactly. Like some landing gear parts. The document mentions aluminum alloys and chrome molybdenum steel are preferred there.
And malleability, that's more for the skin.
Absolutely, for forming those curved sheet metal parts, fuselage, wings. It really shows the ingenuity in material selection.
Matching the metal's basic character to what the part actually needs to do.
Right, so you need something that can take a beating, basically, and can be shaped without cracking.
Okay, but how do they even tell different steels apart? There has to be more to it than just, looking at them.
That's a really good point about identification.
Yeah.
There's the formal system, the SAE numerical index, classifying them by composition.
Okay, the official way.
But technicians also have some, well, pretty ingenious field methods for quick IDs.
Like what?
One fascinating one is spark testing. You hold the steel against a grinding wheel.
And watch the sparks. Seriously.
Yeah, by observing the pattern. The color, the length, the branching experienced techs can get a rough idea of the steel type.
No way.
Higher carbon usually gives a wider strain with more sprigs or bursts. Nickel steel might show little white blocks of light in the sparks.
It's like a metallic fingerprint.
It really is. Kind of a testament to the practical knowledge built up in the field.
That's incredible, like a blacksmith's art, but for high-tech machines. Reading the metal's signature, okay, so they can ID the steel. What about making it do what they need? That's where heat treatment comes in, right?
Exactly. Heat treatment is all about controlled heating and cooling to change the metal's internal structure.
And therefore its mechanical properties.
Right. You might want to make it harder, more wear-resistant, or stronger for bigger loads.
Or maybe more ductile so it bends instead of breaks.
Or more resistant to impact, yeah. But it's often a trade-off. Making it harder can sometimes make it more brittle.
Ah, okay. So what are the common methods?
Things like hardening, tempering, normalizing, annealing, and case hardening.
And it works best with alloys, you said, because of the internal structure.
That's right. It's the alloys, those mixtures of metals that respond best because their structure can actually be changed more dramatically by heat. Pure metals don't really react the same way.
Like baking a cake, the different ingredients, the alloying elements, react to the heat to get the final result.
Great analogy. That's exactly it.
So alloys are more shape-shifting on a molecular level with heat. Now, this isn't just, sticky metal in a campfire, is it? What kind of kit are they using?
No, definitely not. Precision is absolutely key here. They use specialized furnaces.
With fans, maybe, for even heating?
Some have circulating fans, yes.
Okay.
And they even use salt baths, molten salts heated to very specific temperatures.
Salt baths. Wow.
Yeah, they offer incredibly precise temperature control over a wide range, from a few hundred up to over 2,000 degrees Fahrenheit.
And measuring that temperature accurately must be critical.
Absolutely. They use pyrometers, often working with thermocouples.
Those little devices with two different metals.
Exactly. They generate a small voltage that corresponds directly to the temperature. Different types for different ranges, always aiming for accuracy.
Okay, so fancy ovens, super accurate thermometers. What's the actual process like? Heating, cooling? What's happening microscopically?
Well, when you heat steel, you're aiming to change its internal crystal structure. You're transforming something called perlite into austenite.
Perlite to austenite. Got it.
Think of perlite as layered and austenite as more uniform. It's like rearranging building blocks.
And that takes time.
It does. So slow. Even heating is really important.
Yeah.
Sometimes they preheat below the final temperature first, then bring it up slowly to avoid shocking it.
Makes sense. And the cooling, quenching.
The cooling rate, or quenching, has a dramatic effect on hardness. They use different liquids, oils, water, brine. Each cools at a different speed.
Faster cooling means harder steel.
Generally, yes. Rapid quenching is key for hardening, but it comes with risks.
Like warping or cracking.
Exactly. Internal stresses can build up. That's why sometimes they agitate the liquid or use pressure sprays for more uniform cooling.
Okay.
And crucially, hardened steel is often very brittle. So it needs tempering immediately after quenching.
Tempering? What does that do?
Tempering involves reheating it, but to a lower temperature. It reduces some hardness, but significantly increases toughness. It's finding that balance.
So tempering is like calming it down after the shock, making it more usable.
Gotcha. And what about case hardening? I saw that mentioned.
Case hardening. That's a clever technique. You create a hard, wear-resistant outer layer, the case, while keeping the inside, the core, tough and strong.
Like giving it a tough skin, but a resilient interior.
Exactly. Perfect analogy. Ideal for parts needing a durable surface, like gears or bearings, but that also need to handle loads without breaking.
And then it works best on low-carbon steels. Low-carbon and low-alloy steels, yeah. If you case hardened high-carbon steel, the hardness goes right through, making it brittle. The process actually changes the surface chemistry, adding carbon or nitrogen, while the core stays the same. Creates a hardness gradient.
Tough skin. Soft heart. Great way to think about it. Now, after all this careful heating and cooling, how do they know they actually hit the target hardness? They can't just guess, right?
Absolutely not. That's where hardness testing comes in. The Rockwell hardness test is very common.
How does that work?
It presses an indenter, either a hard diamond cone or a spiel ball, depending on the material, into the metal surface under a specific load.
And measures the dent.
Essentially, yes. The depth of the indentation gives you the hardness number. There are different Rockwell scales, A, B, C, etc., using different penetrators and loads for different hardness ranges.
Diamond for harder materials, steel ball for softer?
Exactly. And interestingly, you can't directly Rockwell test really thin stuff like clad aluminum sheets accurately. Because the indentation would go through the thin, hard cladding and be affected by the softer core underneath. You'd need micro-hardness testing for that.
Interesting. Okay, that's a solid grounding in ferrous metals. Let's shift gears now. Non-ferrous metals, starting with the real aviation workhorse for lightweighting. Aluminum.
Aluminum is definitely a workhorse, and for good reason. Pure aluminum is naturally light, malleable,
Easy to shape.
ductile, can be drawn into wires, and it's corrosion resistant. But it's the alloys that really unlock its potential for aircraft structures.
Mixing it with other metals.
Right. Small amounts of copper, magnesium, silicon.
Mm-hmm.
These give aluminum alloys that fantastic strength-to-weight ratio.
Strong, but light, crucial for flight.
And generally easy to work with in manufacturing. But there's a catch.
Oh.
Adding some elements like copper boosts strength but can make the aluminum more susceptible to corrosion, so it's often a balancing act.
Strength without the extra pounds sounds ideal for things that fly. And there's a whole system for naming these alloys, right? It's not just strong aluminum.
No, definitely not. Wrought aluminum alloys, the ones worked mechanically, like rolled or extruded, use a 4-digit index system.
What do the digits mean?
The first digit tells you the main alloying element. 1XX is mostly pure aluminum. 2XX series uses copper high strength, but less corrosion resistant.
Okay.
3XX uses manganese moderate strength, good workability. 4XX uses silicon, often for welding. 5XX uses magnesium, good welding, and corrosion resistance, but you have to watch out for stress corrosion, cracking with high temps, or too much cold working.
Right.
And the 6XX series has silicon and magnesium heat treatable, medium strength, good forming, generally corrosion resistant. The other digits give more specifics on the exact recipe.
So each number gives you clues about the recipe and what it's good for. And like steel, aluminum can be heat treated too.
Absolutely. Heat-treatable alloys are heated to dissolve the alloying elements uniformly, then quenched rapidly, usually in water.
To freeze them in place.
Exactly, in a supersaturated solid solution. Makes the metal soft and unstable initially. Then it undergoes age hardening. At room temperature, that's natural aging. Or at higher temps, artificial aging. The dissolved elements precipitate out as tiny particles.
And those particles make it stronger.
They act like obstacles to movement within the metal's crystal structure, making it stronger and harder. There's also a system for temper designations.
Like T4 or T6?
Right. They follow the alloy number. O's is annealed, softest. H is strain hardened. WNE is solution heat treated, but unstable, still aging. T4 and T6 are specific artificial aging treatments for different strength levels.
Okay, lots of ways to tweak aluminum. What other non-ferrous players are big in aircraft materials?
Magnesium's really interesting. It's the lightest structural metal out there, about 2/3 of the weight of aluminum.
Wow.
Alloyed with zinc and aluminum, it gives an incredible strength-to-weight ratio, good for secondary structures where weight is critical.
And titanium.
Titanium looks a bit like stainless steel. It has a unique spark test, brilliant white burst, and it'll leave a dark line if you draw it on glass.
Why is that?
Formation of titanium oxide. Its properties elasticity, density, high temp strength fall between aluminum and stainless steel. And it's very resistant to stress corrosion cracking. Big advantage.
So magnesium for ultimate lightweighting, titanium for when you need something tougher than aluminum that handles heat well. What about copper alloys?
Copper shows up mainly as bronzes.
Okay.
Copper and tin and aluminum bronzes, which are copper and aluminum alloys.
Are aluminum bronzes common?
They are, particularly in aircraft. High strength, excellent corrosion resistance air, salt water, chemicals. Strength can be comparable to medium carbon steels, used in bushings, bearings, hydraulic parts.
Interesting. So it's not just alloying and heat. The outline mentioned cold working for aluminum too. What's that about?
Cold working or strain hardening is another key way to strengthen aluminum. It's physically deforming the metal at room temperature, rolling, drawing, forging.
How does that strengthen it?
The deformation creates imperfections, dislocations in the crystal lattice. They get tangled up and stop further movement, making the metal harder and stronger.
And that's the H temper designation.
Exactly. The H after the alloy number means it's been strain hardened. Different H numbers indicate the degree of hardening.
So physically working it makes it tougher. And I also saw precipitation thermal treatment. Is that just artificial aging again?
Yes, precipitation thermal treatment is basically another term for artificial aging. It's that controlled heating process after solution heat treating to encourage those strengthening precipitates to form.
Controlled precipitation.
Right. And some alloys continue to age a bit naturally at room temp afterwards, but artificial aging gives much finer control over the final properties.
Okay, that's a good overview of the metallic building blocks. Now, let's move into the fascinating world of composites and non-metallic materials. It's definitely not all metal these days, is it?
Absolutely not.
Yeah.
Composites are fascinating. Engineered blends of different materials to get properties you can't get from just one.
Like a reinforcement held in a matrix.
Exactly. Reinforcement, like fibers or particles, held by a matrix, often a resin. The key is the individual parts remain identifiable, mechanically separable, at least in theory.
Concrete is an example, right? Aggregate and cement.
Perfect everyday example. In aircraft, we're often talking reinforced plastics, strong fibers, embedded in a plastic resin matrix.
Reinforced plastics, like for radomes, those nose cones, and wingtips. What makes them so good for that?
They are indeed used there. They're typically thermosetting materials. They cure chemically, irreversibly.
Can't be remelted.
Right. They have excellent dielectric properties, don't conduct electricity well. Ideal for radomes, letting radar signals pass through.
And strong but light.
Very high strength-to-weight ratio, often better than metals. Good resistance to mildew, rot. Relatively easy to form into complex shapes.
So radomes, antenna covers, wingtips, interiors, insulation.
Exactly. They can be solid laminates, layers bonded together, or sandwich-type laminates.
Sandwich, like a core between skins.
Yes, a lightweight core between thin, strong outer layers, often made with contact pressure resins that cure under low pressure. Simplifying things, curing usually needs a catalyst like benzoyl peroxide.
Okay, so the resin is the glue. Reinforcement gives strength. What are the common resins? Sounds like there's more than one flavor.
Oh, there's a diverse range, each with its own profile. Polyester resins are generally cheaper, process fast. Low smoke types for interiors are good for safety.
Okay.
Vinyl ester resins have better corrosion resistance and mechanical properties than standard polyesters.
A step up.
Then you have epoxy resins, a real workhorse for high-performance composites. Slower processing, often need heat to cure, typically 250, 350 degrees to a knit.
Why the heat?
Allows for superior strength and stiffness to develop. Used in demanding applications, advanced manufacturing like autoclaves, filament winding.
Even for really high temperatures.
Polyon resins excel there, near hot engines, high-speed airframes. But they need very high cure temps and special bagging materials like Kapton or Upolex.
Wow. Then thermoplastics?
Right, unlike thermosets, they soften with heat, harden when cooled. Advantages: faster processing, potential recyclability,
And semi-crystalline thermoplastics.
good balance, flame resistance, toughness, good mechanicals. Increasingly used even in primary structures, often with carbon or aramid fibers.
Sounds like choosing the resin is as critical as choosing the metal alloy, depending on the job. Now, sandwich structures. What core materials go in those lightweight panels?
Sandwich structures are ingenious for stiffness without weight, like an I-beam principle. Common cores include hexagonal honeycomb.
Made of aluminum or Nomex.
Often, yes. Excellent crush strength and stiffness for its weight. There's also flexicore, which is more flexible for curves. An overexpanded core, a variation with better shear properties.
What about foams?
Various foams are used. Polystyrene foam, like styrofoam, easily shaped with hot wire. Phenolic foam is very fire-resistant but usually has lower mechanical properties than honeycomb. Choice depends on weight, stiffness, impact, fire safety needs.
Different cores for different needs. Now, with all these layers, are there common flaws or weaknesses in composites?
Unfortunately, yes. Being complex, imperfections can occur, often at the fiber matrix interface or within the resin parallel to fibers.
Like what kind of flaws?
Micro-cracking, tiny cracks in the resin. More seriously, delaminations, where layers separate. Minor flaws might be okay, but widespread damage or large delaminations definitely weaken the structure.
That makes sense. So how do they find these hidden flaws? Can't just look at the surface, can you?
Not reliably. Non-destructive inspection (NDI) is crucial. Visual check is first looking for whitening, maybe indicating subsurface issues, but it's limited.
What else?
Tap testing or coin tapping. Simple, rapid for large areas.
Listening for the sound.
Exactly. Solid structure rings clearly. A dull thud can indicate a near-surface delamination or void. There are even automated tap testers now.
Okay, that's clever. What about deeper flaws?
Ultrasonics. Send high-frequency sound waves in, analyze the reflections. Bond testers detect delaminations, voids, core disbonds. Pulse echo, phased array, give more detail.
Like medical ultrasound.
Very similar principle. Radiography, X-rays are also used. Good for internal views. Seen crushed core, water ingress, fiber misalignment, flaws parallel to the beam.
But maybe not so good for delaminations flat against the beam.
Generally less effective for those, yes.
It's like having different imaging tools to see inside the aircraft's skin. Now, if they find damage, how do they repair composites? Sounds like a different ballgame than fixing metal.
You're absolutely right. It's specialized. Repairs vary with the damage. For laying up new material, these special hand tools, scissors, pizza cutters for fabrics, squeegees, brushes for resin.
Pizza cutters, nice.
Yeah. And interestingly, with carbon fiber, air-driven tools are often preferred over electric, unless the electric ones are fully enclosed.
Why is that?
Carbon fiber conducts electricity, potential hazard.
Ah, good point. What about pre-pregs, the ones with resin already in them?
Pre-pregs need careful handling. Often stored frozen, need thawing, precise cutting, correct ply orientation, then laid up, vacuum bagged, cured under heat, usually in an autoclave or oven.
Vacuum bagging seems important.
Crucial for consolidation, removing trapped air between layers.
Yeah.
Ensures a strong, void-free repair.
So lots of precise steps. What about the actual layup techniques? How do they ensure a strong repair?
Precision is everything. They often use ply locating templates like stencils for correct placement and shape.
Okay.
Taper sanding around the damage creates a gradual slope, feathers the repair, plies in smoothly, helps distribute load.
Right, avoid stress points.
Exactly. Controlled bleed techniques manage resin content in wet layups where you add resin to dry fabric, ensuring the right fiber to resin ratio. Edge bleed out for horizontal wet layups removes excess resin.
And ply orientation.
Absolutely critical for strength and stiffness. Fibers must align with stress directions. They even use a warp clock, a visual aid, to get the warp fibers oriented correctly per specs.
Sounds incredibly meticulous, like tailoring with advanced fabrics. How do they get the resin evenly into the fabric, if not using prepreg?
Couple of main ways. The traditional brush or squeegee method, manually applying resin to fabric laid on a release film or cowl plate.
Okay.
Or the vacuum bag method, often preferred for tight weaves or precise resin ratios. Lay up dry fabric, cover with release and bleeder cloth, seal under vacuum. Vacuum draws resin through, ensuring good wet out, less trapped air. Higher quality laminate.
Vacuum bagging again seems vital. What about pressure during the cure? Always needed.
Yes, pressure is generally essential for a strong consolidated bond. C-clamps with pressure pads for solid laminate edges. Spring clamps sometimes.
But mostly vacuum bagging for larger areas.
It's the most common way for uniform pressure. Atmospheric pressure pushes down evenly under the bag.
And for heated cures.
Absolutely critical to monitor the part temperature with thermocouples. Big composite parts act as heat sinks. Their temp can lag behind the oven. Accurate monitoring ensures proper cure.
Good point. The material itself absorbs heat. Now, what about installing patches onto the structure?
After debulking, applying vacuum pre-cure to remove air. There's often limited time to form the patch to the aircraft contour.
Use adhesives.
Typically, film or paste adhesives bond the patch, then vacuum bag, often a heater blanket, for pressure and temperature to cure the adhesive.
What about pre-made patches?
External repairs with pre-cured patches are possible. Less flexible, so better for flatter surfaces. Bonding process is similar surface prep, adhesive, vacuum, heat.
Are bolted repairs ever used?
They are, but generally less desirable for honeycomb structures. Thin face sheets have limited bearing strength around holes, but sometimes necessary or preferred. Specific hole prep and fastener procedures apply then.
So bonding is preferred, but bolts have a place. What about removable composite panels, like access doors? How are they attached?
Usually screws with nut plates. Various types exist: rivetless, adhesive bonded, avoiding extra holes in the composite. Allows secure, repeatable fastening.
Okay, screws and nut plates for access. Now, drilling or countersinking composites different from metal.
Significantly different. Composites can splinter or delaminate easily, need specialized techniques.
Like what?
Carbide cutters, very sharp. Slow, constant feed rate minimizes heat. Fiber pull-out. Drill guides for precision.
Any issues drilling through composite into metal underneath?
If drilling into titanium,
Yeah.
risk of chip pull-through, damaging the composite on exit. Might need final reaming. Carbide reamers, often used for final sizing in carbon epoxy, need backside support to prevent splintering.
Cutting fluids.
Usually not recommended for thinner composites, can be absorbed.
And countersinking for flush fasteners.
Specific angles, 100 or 130 degrees, match the fastener head. Controlled radius cutters recommended for proper fit, avoiding stress concentrations.
Sounds like you need a delicate touch and special tools. And safety must be important with all these fibers and chemicals.
Absolutely crucial. Eye protection, always debris, chemical splashes. Respiratory protection is equally vital.
Carbon fiber dust. Resin fumes.
Exactly. Carbon dust is an irritant. Fumes from resins, adhesives, good ventilation, local exhaust, dust masks or respirators with correct filters are essential. Always follow the safety data sheets for all materials.
Safety first. Okay, the outline mentioned forming acrylic plastic too. How does that fit in? Windows and canopies.
You're right. Acrylic plastic plexiglass, lucite used for windows, canopies, good optics, lightweight, easy to form.
How do they shape it?
Becomes pliable at low temps, needs little pressure. So mold can be simple wood, plywood, plaster. Key is the mold surface must be perfectly smooth.
Any bumps will transfer.
Readily. And molds need ways to hold the plastic snug during cooling to prevent warping and ensure it keeps the shape.
Simple molds for complex curves. And finally, cementing composites. What's that about?
Usually refers to polymerizable cements, specialized adhesives, curing chemically joining composite parts.
Anything special about them?
They often shrink slightly as they cure. So you might pour slightly above the surface, then machine or sand flush after cure. Small bubbles during cure are sometimes unavoidable, often not a concern if the surface is trimmed later.
All right, a comprehensive look at composites and non-metallics. Let's shift now to a material with a long history. Wood. Not common in airliners, but still flying, right?
Indeed. Wood played a huge role early on, even into WWII. Think of the de Havilland mosquito.
The wooden wonder.
Exactly. Or the massive Hughes H-4 Hercules, the spruce goose. While not primary structure in mass-produced modern planes, many older wooden aircraft are still operating, maintained by dedicated owners.
And people still build and store them.
They do. For history, education, recreation, flying classic designs.
Amazing they're still airworthy. What do inspectors look for on a wooden aircraft?
Keen eye needed. Focus on contours, alignment wing leading trailing edges. Distortion, sagging, waviness can mean internal deterioration needing closer inspection.
And the fabric covering?
Splits or tears need investigation. Check the underlying plywood or solid wood condition.
So, look for things out of shape, visible damage suggesting deeper issues. What causes wooden aircraft to deteriorate?
Several factors. Fungal growth rot, mildew is a big one, especially in damp conditions.
Wood is food for fungi.
Right. Temperature-humidity cycles cause swelling, shrinking, weakening glee joints, causing cracks, and even dark paint.
Dark paint? How?
Absorbs more sun, higher skin temps, can weaken adhesives over time.
So watch out for moisture fluctuations and maybe rethink that cool dark paint job. What specific wood conditions are red flags?
Signs of decay, discoloration, often darker, softening when probed. Dry rot is a misnomer. Decay always needs some moisture.
Okay.
Dark gray stains following the grain suggest water penetration. Also look at grain structure. Mineral streaks are usually okay if no decay.
What's not okay?
Cross grain, wavy curly interlocked grain, hard knots or pin knot clusters disrupting grain flow, these compromise strength. Spike knots too.
To not just rot, but the wood's inherent quality and grain are critical. Now, glue is fundamental. What's important when choosing and using glues for wood?
Selecting the right adhesive is paramount. Always consult the aircraft manual. Look for glues meeting standards, mil-spec, AMS, TSO.
Okay.
Understand the glue's working times, open assembly time, glue applied to parts joined, closed assembly time, time under pressure for initial bond.
Preparation matters too.
Essential. Wood clean, dry, free of contaminants. Apply glue as a thin, continuous film to both surfaces, and crucially, even pressure during the entire cure.
How do they apply pressure?
Clamps, straps, weights, vacuum bags, even temporary brads, nails, screws, or power presses.
And how do you know if the joint is good afterwards?
Testing. A proper joint should fail in the wood fibers when stressed, leaving wood fibers on both sides of the break, not a clean glue line failure.
Careful science, right? Adhesive, meticulous prep, correct application, consistent pressure, verification. What about repairing specific parts like wing ribs or spars?
Yes, specific procedures apply. For wing ribs, damage at intersections often needs reinforcing with plywood gussets glued across the joint. Damage over a spar might get a continuous gusset over the spar onto the cap strip.
And wing spars themselves, the main beams.
Locally damaged sections are replaced with fitted filler blocks, reinforced with full-width doublers glued to the sides, extending beyond the repair. Importantly, no nails or screws in primary spar repairs, they weaken the wood.
No nails or screws, got it. Longitudinal cracks.
Clean the crack, glue plywood doublers along the sides to bridge and reinforce. Damaged bolt holes can be drilled out, new bushings glued in.
Okay. What about plywood skin damage?
Depends on size and location. Minor damage, maybe a fabric patch, slightly larger, a splayed patch, bevel edges of damage and patch for a wider glue surface.
The spatch.
For thin skins between framing. Trim damage, fit patch, bevel edges, glue. Often needs doublers inside. Pressure from weights or temporary screws.
Thicker plywood.
Plug patch, circular oval replacement, or scarf patch, complex angled joint for large glue area. Depends if you can access the back for doublers pressure.
Blend of woodworking and aviation know-how. Once repaired, sealing and finishing.
Absolutely essential. Prevent moisture ingress. Seal margins, exposed wood with moisture-resistant coatings, varnish, lacquer, or increasingly, epoxy coatings.
Interior surfaces too.
Yes, often a thin first coat of varnish to penetrate, then full coats. High moisture areas might get an extra luminized sealer coat.
Creating a barrier against moisture. Lastly, fabric covering. Why is it still used? How's it maintained?
Still viable, even preferred for some types of older designs, some light aircraft. Recovering is accepted maintenance. Modern systems often use polyester fabrics, non-dope finishes, durable, resist cracking, can last decades.
Legal requirements.
Generally must use original equivalent materials techniques unless you get specific FAA approval for alternatives.
Installation details.
Inspection rings installed for access later. Wood frame needs primer, gope proofing, often two-part epoxy, before fabric goes on. Fabric attached by stitching and adhesives.
Rib lacing.
Specific stitching pattern spacing secures fabric to ribs. Knots hidden to prevent chafing. Then coatings. Sealers fill weave. UV protection fill coats, often with aluminum. Final color paint.
Highly skilled craft, traditional techniques, modern materials. Okay, wrap on wood. Let's move to something affecting all aircraft. Corrosion. What is it exactly? Key factors.
Simplest terms. Metal deterioration due to reaction with its environment. Chemical or electrochemical. Several factors needed.
Like?
Anodic-cathodic areas on the metal potential difference.
Yeah.
Often happens with dissimilar metals in electrical contact.
Don't need an electrolyte too.
Yes, a conductive substance, often water with salts or acids. Oxygen plays a role in many types. Even biological organisms, bacteria, fungi can contribute.
Anything else?
Mechanical stress, exposure time, even lead or graphite pencil marks on aluminum can accelerate it.
So a chain reaction sped up by materials and environment.
Right.
What are the different types of corrosion on aircraft? Sounds like more than one way for metal to degrade.
Oh, there's a whole spectrum. General surface corrosion, uniform etching or pitting, galvanic corrosion to similar metals, electrolyte, one corrodes faster. Concentration cell corrosion, often due to oxygen differences. Under gaskets, dirt, faying surfaces, crevices, stainless steel can get this.
Active passive cells.
Break down to protective passive films, like on stainless, often started by salt deposits. Pitting corrosion, localized small pits or holes.
Intergranular.
Attacks along grain boundaries inside the metal can weaken significantly without much visible surface damage. Insidious.
Exfoliation.
Type of intergranular and layered structures. Metal separates in layers like peeling pages.
Stress corrosion cracking. Sounds bad.
Particularly dangerous. Tensile stress plus corrosive environment leads to cracks. High-strength steels, some aluminum alloys susceptible in salt solutions, titanium in specific environments like methanol HCl, magnesium in moist air.
Fatigue corrosion.
Cyclic stress plus corrosion reduces endurance limit, fails at lower stress.
And fretting corrosion.
Surface damage from vibration, slight movement between close contact surfaces.
Quite a list. What visual signs might an inspector look for?
Various forms. Uniform roughening, edging, distinct pits. Blistering paint is an early sign of corrosion underneath. Scaling, flaking, where corrosion products detach. Powdery residue.
Intergranular might not be obvious.
Not always on the surface, but severe cases might look weakened, powdery if disturbed. Exfoliation shows as lifting or bulging surface layers.
So anything looking deteriorated, flaking, unusual buildup is a potential red flag. What are common culprits, the substances or environments causing corrosion?
Acid, sulfuric from batteries, hydrochloric from pollutants, alkalis, salts, especially sodium chloride, salt water, big factor near coasts or where de-icing salts used.
Atmosphere itself.
Yes, especially with pollutants like sulfur dioxide, even pure water over time. Engine exhaust has acidic compounds. Biological growth creates corrosive spots.
So it's the metal and its exposure. Primary strategies to prevent or control it must be a constant battle.
It is. Prevention starts at design material selection, minimizing dissimilar metal contact, choosing resistant alloys.
Coatings are key.
Cornerstone. Paint systems, anodizing for aluminum, plating, corrosion inhibitors applied as films or added to fluids.
Environmental control.
Proper ventilation, dehumidification, drainage to prevent moisture buildup. Regular cleaning removes contaminants. Lubrication prevents fretting. Essential maintenance.
Layered defense. What about dissimilar metals in contact? How do you minimize galvanic corrosion?
Several ways. Best is an insulating barrier, non-conductive washer, gasket. Coating breaks electrical contact. Compatible coatings on both metals help isolate them.
Sacrificial anodes?
Yes, a more anodic metal connected electrically. Corrodes preferentially, protecting the main part. And choosing materials closer on the electrochemical series helps.
Like titanium fasteners with carbon composites instead of aluminum.
Exactly, more compatible.
Sacrificial anodes, designated lambs. What specific areas on an aircraft are corrosion hotspots needing extra vigilance?
Several notorious ones. Battery compartments, acid spills, fumes, engine exhaust trails. Bilge areas trap moisture contaminants. Wheel wells, landing gear moisture, salt, debris.
Control cable penetrations.
Can let moisture in. Fuel tank bottoms, water condensation. Around fasteners, especially dissimilar metals or failed sealant. Gano hinges trap dirt, moisture, often dissimilar metals. Engine fronts, pollutants, moisture. Electronic compartments if not sealed well.
Sounds like anywhere moisture and contaminants gather or different materials meet, any in-service factors making it worse.
Absolutely. Operational stresses, residual stresses from manufacturing or repair make metals more susceptible, especially stress corrosion cracking, fatigue corrosion.
Carries new welds.
Often more vulnerable. Microstructure changes, coating disruption, possible corrosive flux residue. Even minor repairs, if done wrong, can create corrosion sites like scratching a coating and not touching it up.
So operations and maintenance history matter. What about protective platings like cadmium or chromium? Can they corrode?
Yes, if compromised. Cadmium, zinc are sacrificial, great protection, but susceptible to acids, degrade over time. Chromium, nickel resist well, but if scratched or damaged, base metal underneath can pit, corrosion spreads under the plate.
And clad aluminum.
Relies on the pure aluminum outer layer. Effective as long as intact. If damaged significantly, the underlying high-strength alloy is vulnerable.
Okay, good understanding of corrosion. Let's move to holding it all together. Fasteners. More than just standard nuts and bolts, right?
Yeah, absolutely. Fasteners are critical, dual purpose. Allow quick dismantling replacement for maintenance and provide structural integrity, stiffness for flight loads.
Reliable and maintainable. Let's start with the basics. Bolts, studs, screws, key differences.
Bolts typically used for high strength, blunt threaded end for a nut. Aircraft types, AN, NAS, MS prefixes. Various heads, hex, clevis, shear, eye bolt, internal wrenching, countersunk.
Identification markings.
Yes, on the head. Manufacturer, material, standard special purpose. Raised recessed marks, maybe colored lacquer for inspection status. Critical is correct grip length, unthreaded part matches material thickness.
Right.
Standard self-locking fiber collar, spring action, anchor nuts permanently attached. Pell nuts, secondary locking.
Screws and studs.
Machine screws have closer tolerances. Aircraft specs. Studs are headless bolts, threaded both ends, standard or shouldered, used for attachments, pivots. Self-tapping screws cut own threads in softer materials.
Sounds like a specific bolt for almost every need. In flight vibration, how do they stop shaking loose?
Ingenious locking devices. Tab washers, spring washers provide friction. Locking plates bend over nuts bolt heads. Split pins, cotter pins, go through holes bent over.
Wire locking.
Very common. Safety wire connects 2 or more fasteners, physically stops them unscrewing. Quick release fasteners like airlocks for frequently opened panels. Keys, circlips prevent axial movement. Shake-proof lock washers bite into fastener and workpiece.
Whole arsenal of gadgets to keep things tight. Washers seem basic, but different types.
Definitely. Plain washers, AN960, AN970, distribute load, prevent damage. AN970 is wider, often for wood to prevent crushing. Lock washers prevent loosening. Special washers for sealing specific shapes.
Sheet spring nuts.
Lightweight, self-locking for thin sheet metal. Sealing net plates have built-in seals. Captive fasteners stay attached to panels, even when undone.
So even washers have specific jobs. Now lock bolts seem different. What are they? Were used?
High strength, 2-piece, very strong, permanent connection. Often in primary structures, needing reliability under high load. Vibration.
How do they work?
Pin, like a bolt, and a separate collar. Special tool pulls the pin, clamps parts tight, simultaneously swages, deforms, collar into pin grooves, creating mechanical lock. Excess pin breaks off.
Different types?
Pull type, stump type, pin breaks at set point. Blind type for one-sided access. Grip range material thickness is crucial for selecting correct pin length.
More permanent, high-strength alternative. What about special shear and bearing load fasteners? Examples?
Specialized for specific loads. Pin rivets are mainly for shear loads. Caper lock fasteners use tapered pin collar for interference, fit exceptional shear bearing strength, often in high-stress areas. High-strength bolt spins, aluminum, titanium, stainless. Rolled threads improve fatigue life. Sealing on sealing collars.
Others?
Dill lock screw rivets, internally threaded blind fasteners. Deutsch rivets, high-strength blind. Stainless sleeve, steel pin. Often in modern structures needing blind install, high strength.
Array of specialized fasteners for specific demands. Installing nuts, washers, bolts best practices, pitfalls.
Absolutely. First, correct size bolt for hole. And end bolts have some clearance. NAS, clevis bolts, often closer tolerance, light drive fit.
Material matters.
Crucial. Use correct bolt nut material per specs. Use washers under head and nut generally. Distributes load, prevents galling. Type of washer must match materials, conditions.
Direction.
Good practice. Install bolts head up or facing forward. Prevents falling out if nut loosens. Proper safety wire locking essential for critical fasteners.
Damaged threads.
Can often repair internal threads with helicoil inserts. For slightly oversized holes, non-critical, maybe an Acres sleeve. Thin bushing for smaller bolt.
Lots of small details add up. Finally, rivets. Solid shank, bucked versus blind, one-sided access. Key differences.
Right. Solid rivets for primary structure repairs, high strength, reliability. Identified by material, head type, shank size, length, temper. Common heads, universal, round, flat, countersunk, brazier.
Mercurial.
Mostly aluminum alloys, 1100 pure, 2117T common, higher strength 2017T, 2024T.
Icebox rivets.
That's 2017T, 2024T. A dealed soft for driving, kept refrigerated till used to start them age hardening too fast. Temper condition indicates heat treatment state, strength.
Wind arrestant.
For one-sided access. Friction lock, mandrel held by friction, or mechanical lock, mandrel mechanically locked for higher strength, stops it falling out.
Examples.
Cherry lock, chair easy, bucky, self-plugging rivets. Plug stays in body, robust, often sealed. Various materials. Aluminum, Monel, stainless steel. Choice depends on materials joined, environment.
Solid for strength with access, blind for limited access. How ensure right size rivet.
Length and diameter. Length measured under, head to end. Solid rivets need enough length for proper bucked head. Blind rivets depend on grip length, material thickness. Use grip gauges, diameter based on hole size, strength needed, head style based on application, aerodynamics.
Installation tips. Driving solid versus pulling blind.
Driving solids varies by material. Softer aluminum, easy. Harder alloys, steel need more force, controlled technique. Steel rivets sometimes need heating first.
Corrosion.
Always consider especially dissimilar metals. Even different aluminum alloys can cause issues. Compatibility is key.
Blind rivets.
Correct. Grip length critical. Specific tools needed for different types. Follow manufacturer instructions. Various head styles, too.
Okay, thorough look at fasteners. Let's move to fluid gas systems. Pipes and unions. Common tubing materials.
Primarily aluminum alloy and steel. Aluminum alloy for lightweight, good formability. Steel for high pressure, strength, temperature resistance.
Identification.
Aluminum alloy tubing often has colored bands. Different colors combinations indicate alloy, sometimes intended use.
How are tubes connected? Different fittings for pressure, disconnection needs.
You're right. Two main categories, flared and flareless fittings.
Flared.
Often A in type. Use sleeve and nut. Tube end flared precisely. Nut tightens, compresses sleeve against flared, creates seal. Common in low, medium pressure hydraulic fuel systems.
Wireless.
For high pressure, high vibration. Body, sleeve, ferrule, nut. Tightening forces sleeve to bite into tube outer surface. Strong grip, reliable seal. Common design is reverse angle, distributes stress well.
Bulkhead fittings.
Universal bulkhead fittings allow tubing through panels to secure sealed connection both sides.
So flared for general use, flareless for high stress pressure. What about flexible connections? Aircraft use hoses too, right? Especially for movement.
Absolutely. Flexible hose assemblies are essential. Connect moving parts, absorb vibration, accommodate tolerances. Used in low, medium, high pressure systems.
Materials.
Typically rubber or Teflon, PTFE, with braided reinforcement layers. Fittings can be reusable, detached from old hose, attached to new, or permanently attached, Krumpstwedged. Hoses often have ley line markings along length manufacturer, type, pressure rating. Medium pressure might use spur and nipple socket fittings.
Variety of hoses and fittings for fluid, pressure, movement needs. Other conduits tubing on aircraft.
Beyond fluids, there is electrical conduit protecting wiring. Instrument air tubing, small metal plastic for pneumatic systems. Specialized tubing, too.
Like?
Rocket oxidizer, breathing oxygen, fire protection, fuel, de-icing, lubrication, avionics coolant, hydraulic power. Each designed for specific fluid gas properties, temps, pressures.
Complex network of pipes, hoses, conduits. Let's move to things providing springiness, absorbing shocks. Springs. Main types.
Primary types. Spiral springs, compression, resist squashing, extension, resist pulling, torsion, resist twisting. Also leaf springs, typically in landing gear for impact absorption.
Materials used. Must withstand repeated loading.
Common materials. Carbon steel, chrome vanadium steel, better fatigue life. Chrome silicon steel, even higher fatigue life, resists permanent set. Stainless steel for corrosion resistance, good creep resistance at high temps.
Manufacturing.
Hot or cold winding, depending on wire size, desired properties. Hot winding, often for thicker material, allows stress relief after winding.
So materials chosen for strength, fatigue, environment. Key dimensions and characteristics engineers consider?
Key dimensions: wire diameter, coil diameter, free length, unloaded, no end treatment. Number of coils, pitch, distance between coils.
And treatments?
Vary a lot. Plain ends, ground ends, flat bearing surface, hooks, extension, loops, extension, torsion.
Characteristics.
Type of load, compression, extension, torsion, size, weight, material, pre-post winding treatments, stress relief setting for desired performance.
Precise engineering for a reliable spring. Moving on to things allowing rotation bearings. Primary types.
Main types: plain bearings, bushings, sleeves, and rolling element bearings, ball bearings, roller bearing.
Vane bearing.
Lower speed, lower load. Simple, cost-effective.
Ball bearings.
Hardened balls between races reduce friction. Good for radial and moderate thrust loads.
Roller bearings.
Cylindrical or tapered rollers. Higher load capacity than same-size ball bearing. Good for radial loads. Some handle significant thrust too.
What loads are they best for? Design dictates strength.
Exactly. Plain bearings mainly handle radial loads, perpendicular to axis, rely on lubricant film.
Ball bearings.
Versatile. handle radial and some thrust loads parallel to axis.
Roller bearings.
Larger contact area, better for heavier radial loads than same-size ball bearings. Capered roller bearings specifically designed for significant thrust, plus radial loads like wheel bearings. Specialized designs handle combined loads.
Choice depends on loads, operating conditions. Now, transmitting power, transmissions, common gear types in aircraft.
Several types.
Yeah.
Spur gear straight teeth, simple parallel shafts. Helical gears angled teeth, smoother, quieter than spur, also parallel shafts.
Bevel gears.
Teeth on conical surface, transmit power between angled shafts often 90 degrees.
Worm gears.
Screw-like worm meshes with worm wheel. Very high gear reduction ratios, used where large speed difference needed.
How are these arranged in transmissions for speed reduction torque multiplication?
Simple arrangements. 2 gears, or
That's
complex. Compound gear trains, multiple gears in series, for larger ratios. Planetary gear arrangements are interesting.
How do those work?
Central sun gear, planet gears meshing with sun, held in carrier. Outer ring gear meshing with planets. Holding one element, driving another gives various ratios compactly.
Common use.
Reduction gearing between high-speed engine and slower propeller. Allows engine efficiency, keeps prop tips subsonic.
Gear lash and tooth contact pattern were mentioned. What are they? Why critical?
Gear lash is clearance backlash between meshing teeth. Need some for thermal expansion, tolerances, lube film. Too little binds overheats, too much causes noise, impact wear.
Contact pattern.
Area of contact between teeth under load, ideally centered. Improper pattern means misalignment or bad geometry. Uneven load, stress, premature wear failure.
So critical for efficiency, lubrication, long life.
Absolutely.
Yeah.
Especially in transmissions with changing loads direction.
Delicate balance for smooth engagement, lubrication, even forces. Other power transmission methods? Belts and pulleys.
Used in some lighter aircraft like microlights. Engine to prop, often step-down ratio. Also some piston helicopters.
Yeah.
Crankshaft to rotor accessories. Chains and sprockets less common for primary power now, maybe auxiliary systems.
Okay, gears, belts, chains. Now, controlling the aircraft, control cables, typical construction.
Designed highly flexible, strong, multiple strands of high-strength steel wire twisted into strands, then strands twisted into cable.
Designations.
Number of strands, X wires per strand, like
right.
7x7 or 7x19. 7x19 is more flexible than 7x7, good for running around pulleys.
Yeah.
Various diameters for load requirements.
How are they connected? Must have reliable end fittings.
Specialized fittings. Terminals attached to ends swaged, metal fitting compressed on, or threaded.
Thimbles.
Teardrop oval metal loops in cable loop at connection points. Prevent crushing abrasion by bolt shackles. Bishings provide smooth surface through Fairlead's guides. Shackles are U-shaped, removable pin, sometimes for temporary connections or attaching to control horns.
Strong, flexible cables, robust ends. How installed?
Careful routing. Cable guides like pulleys, sealed bearings, minimize friction. Pulleys often have guards to stop cables jumping off. Pulleys supported by brackets attached to structure.
Cable tension.
Critical for responsive control. Adjusted using turnbuckles, right-left-hand threads. Tighten, loosen precisely. Secured with locking devices, safety wire, clips, once set.
Connectors. Spring back.
Cable connectors allow quick disconnect for maintenance. Control surfaces need some spring back, through neutral. Reach stops slightly after cockpit controls. Some systems use rigid push rods instead of cables. Cable drums used for longer runs.
Precise network translating pilot inputs. Let's discuss the electrical system. Wiring and connectors, the nervous system. Common conductor.
Primary are copper and aluminum. Copper, excellent conductivity, heavier. Aluminum, slightly lower conductivity, significantly lighter. Big advantage in larger aircraft for weight saving.
What affects current capacity and pass?
Wire gauge, size, material, copper aluminum, insulation type, ambient temp, altitude, air density affects cooling. Bundling with other wires reduces heat dissipation.
Balance of weight, conductivity, environment matters. What about insulation? Various types.
Yes. Older aircraft might have PVC nylon or Captain. Good high temp, but can be damaged by abrasion moisture.
Newer types.
Advanced materials. Tefsil. Teflon Captain Teflon combos, PTFE, polyimide PFE laminates, superior heat aging, abrasion fluid resistance, insulation rating, max operating temp is critical.
Bundling wires.
Reduces heat dissipation, so current capacity must be decorated per guidelines to prevent overheating.
Newer insulation handles heat damage better. Wires have markings. What info?
Yes, direct marking preferred. Sometimes special marked sleeves. Markings crucial for maintenance troubleshooting. Legible, contrast color. Show gauge, insulation type, often circuit ID code or part number matching diagrams.
Clear labeling essential. Joining wires. How are splices made reliably?
Splices and bundles carefully made, often staggered to avoid bulk. Specific stripping twisting for good contact before permanent joint solder plus heat shrink, or specialized pre-insulated crimp splices, calibrated tool. Splice type must suit wire, gauge, environment.
Staggered splices keep bundles tidy. Aircraft environments are tough. How protect wiring from damage elements?
Chafing protection is major. Grommets where wires pass through holes. Clamp supports secure bundles, stop rubbing. Careful routing away from high heat. Engines, ducts. Proper insulation protects from solvents, fluids.
Inspection.
Clamps check for tightness. Proper installation. Grommets. Sufficient slack needed for movement prevents strain on connections.
Careful routing, clamping, insulation key. Bonding and grounding. Why so important?
Vital for safety, proper operation. Bonding creates low-resistance connections between conductive parts, keeps everything at same potential.
Why?
Dissipates static charge buildup from flight friction, prevents sparks, fuel vapor risk, damage electronics. Static bond resistance, 1 ohm typically.
Ground.
Provides return path for current. References equipment to common ground potential. Bond ground resistance tested, ideally 0.003 ohm for good current flow.
Blotting jumpers.
Short, flexible conductors connecting components. Installed non-interfering, no sharp bends. Clamps preferred over solder on tubes, weakening risk. Clamp material must be compatible, no corrosion. Rated for current if carrying ground return.
Electrical safety, proper function. How keep wires organized for maintenance?
Bundles laced or tied. Lacing cord, nylon straps. Keeps wires neat, prevents chafing. Easier access for techs. But restrictions on lacing, tying in swamp areas, wheel wells, engine nacelles, and high vibration zones could fail or cause chafing.
Neat wiring simplifies things, connecting wires to components, terminal strips, connectors.
Terminal strips join multiple wires. Barriers prevent shorts. Anchored studs for lugs. Bus bars distribute power. Current carried by contact surfaces. Lug strip, not just studs, spare studs often included. A&MS connectors, common for frequent disconnections. Removable parts. Round, rectangular, modular blocks. Environmentally resistant types for harsh areas facilitate maintenance hugely.
Sealing these connections against moisture, contaminants, especially in harsh areas.
Critical for reliability. Connectors often have peripheral seals, compressed when mated, interfacial seals between inserts. Rear needs sealing too.
Yow.
Rear grommets match to wire diameter sealing range. 1 wire per crimp contact recommended for good seal. Heat shrink tubing or potting compound for extra sealing in harsh environments. Spare contacts need plastic plugs to keep moisture dirt out.
Keeping moisture out is crucial. Other final considerations for wiring.
Yes. Allowable voltage drop considered. Ensure enough voltage reaches equipment. Voltage current ratings of all components must be appropriate. Spare contacts and connectors, good for future mods.
Coaxial cable. Location.
Coax for high-frequency signals. Radio. Radar. Location matters. Protect wiring near hydraulic fuel lines from leaks. Swamp areas need extra care routing, support, moisture-resistant components.
All right. An incredibly detailed exploration. We've covered a remarkable amount today, from metal structures to electrical connectors.
We have indeed. Journeyed through metals, composites, fasteners, wiring, even wooden aircraft. Here's the interesting part. You now have a foundational understanding of the diverse materials and hardware vital for safe flight.
Hopefully you picked up some surprising facts like spark testing steel,
Or the icebox rivets.
the heat resistance of polyamide resins, or the meticulous craft of wood repairs. These details offer a real glimpse into aviation maintenance.
For the curious learner like you, this deep dive isn't just facts, it's a framework. Understanding the complexity, the precision behind aircraft engineering and maintenance, you've gained a shortcut to being well-informed.
So what's the big picture? It means there's a vast, intricate world under the skin of every aircraft. We hope this sparked your curiosity to delve deeper.
Maybe into composite repair techniques or the evolution of fasteners.
Consider this. Every single material, every piece of hardware has a story, a reason for being chosen, a critical role. Advancements in materials science keep pushing boundaries.
What new materials, what innovations do you think will shape the aircraft of the future? It's a thought to really let take flight.